Okay, so we're going to solve what I think is a pretty cool problem. It's 2 times the t derivative of u plus the x derivative of u is equal to u. And we're going to have u equals 1 plus x on the non-negative. I think I have, on non-negative. On non-negative x and t axis. Okay, so our curve now is broken into kind of 2 pieces. We have the non-negative x-axis and the non-negative t-axis. So let me just draw what the axis is going to look like here. So let's say this is the x-axis, this is the t-axis. Our curve is just this part right here and this part right here. Okay, and so what's going to happen is basically going to require that we sort of treat each thing separately. And you'll see what I mean as we go on here. Okay, so the parameterization, I'm going to break this into 2 curves. Gamma 1 is going to be the positive t-axis. It's going to be 0, t naught, or the non-negative t-axis, 0 to t naught, for t naught greater than or equal to 0. And then actually, I'm going to call this gamma A for gamma above. It'll make sense. That name will make sense in just a little bit. And then gamma below, x0 comma 0 with x naught greater than or equal to 0. One thing that I do want to point out here is that we need to make sure this function right here kind of is continuous on this curve right there. So it's 1 plus x. If you look at the limit x approaching this way, it approaches 1, and if you look at the t approaching this way, it approaches 1. If there wasn't that consistency condition, then it wouldn't work. So for example, if it was something like, if it was something like e to the t up here, or something if u was equal to e to the t on the non-negative t-axis, and then 1 plus x over here, they would not be in the middle here. It wouldn't be continuous here. Actually, that example it would be, because it would both be equal to 1. If it was 1 plus e to the t going this way and 1 plus x that way, then they would not be equal there at the origin. So for this to really make sense, we need to have this continuity condition there, which we do, because remember, our theorems require that the boundary data, or the curve, or the data on the curve be continuous. Okay, so x prime is going to be the thing that multiplies, I'm going to do that in purple, but I didn't. X prime is going to be the thing that multiplies the x derivative of u, which is 1. Okay, and now we're going to have to be careful on the right-hand side here. So t prime of s is going to be the thing that multiplies the t derivative, that's 2. And then z prime of s is going to be the right-hand side, so that is going to be 0. Okay, now x of 0, we're going to have 2 different curves here. We're going to have the gamma A curve, and we're going to have the gamma B curve. Now for the t-axis curve, x of 0 is going to be equal to 0. T of 0 is going to be equal to t naught. And z of 0, we're going to plug in 0 and t naught to our data here. So it's just going to be equal to 1, because 1 plus 0 is 1. All right, now for the gamma B curve, that's when we are on the positive, or really the non-negative x-axis. Here, x of 0 is going to be equal to x naught. T of 0 is going to be equal to 0. And then z of 0, we're going to plug in these 2 values to our initial data, or not our initial data, but our data on the curve there, which is 1 plus x naught. Okay, now that we have this out of the way, we can go on ahead and start solving for these functions here. And basically, I'm just going to break this up into an XA problem, a gamma A problem and a gamma B problem. So let's see here where I want to write this. So XA of t, XA of s is equal to going to be, the derivative is 1 and the initial point is 0. So XA of s is equal to s. TA of s is equal to s plus t naught. Now z prime of s, what do we have here? Z prime of s is going to be equal to z of 0 times e to the s. So ZA of S is equal to 1, Z of 0 is 1, so it's just going to be e to the S. Okay, so these are going to be the curves that start on the positive t-axis, or the non-negative t-axis. Now in blue, let me do the other one. So XB of S, this is going to be the ones that are starting on the x-axis here. So I'm looking at this data over here. This is going to be equal to S plus X naught. TB of S is going to be equal to S. Now Z of S is still going to be Z of 0 times e to the power of S, but Z of 0 now is 1 plus X naught. So this is 1 plus X naught e to the S. Okay, so let's notice something here. The first thing that I want to point out, I want to look at the characteristic at the intersection. So this gives us the characteristics that start on the t-axis. This gives us the characteristics that start on the x-axis here. I want to see at the middle point here to kind of see if we get the same characteristic, because if we have different characteristics emanating here, it's going to be a little bit challenging. We're not going to be able to do it. So notice that if we look at the origin there, and I look at this example over here, t naught is equal to 0, and so we've got x a of s is equal to x, s t a of s is equal to s, and over here, if I look in the, I'm on the xb, and I look when x is equal to 0, or x naught is equal to 0, xb is equal to s, and tb is equal to s. So in other words, what I'm saying, when I look at the characteristic that is emanating from the origin, it's the same whether I use this formula or this formula. And it really needs to be. If it wasn't, that is, if the initial data was discontinuous, or sorry, not the initial data, if we didn't have these two things match up right, we would have, an over-defined characteristic here, if we had two different characteristics. So what I'm going to do, I'm going to draw, if I look at it, it's going to be a line of slope 1. And so I'm going to draw it kind of alternating, blue and purple, and then of course it comes back through this way as well. This lets us know that it is the characteristic that's kind of a seen here. Okay. So now what I'm going to do is I'm going to look at these characteristics here. Now these characteristics start from a point here on the t-axis. And again, the slope is the ratio of these coefficients, so it's 1, and we're going to have slopes like this. These are going to be the characteristics. I'm going to draw a few of them in the same color, not like I was doing with different colors for previous videos. Okay, so that gives us the characteristics here. For the characteristics starting at the positive x-axis, well, again, there's going to be a slope, lines of slope 1 that go through, whatever x naught is there. So we're going to have lines of slope 1 going like this. Okay, and I hope it's clear that each one of these lines is going to only intersect, aside from this one right here, all of the blue lines are only going to intersect the curve gamma on the x-axis. All of the purple lines are only going to intersect the gamma curve on the non-negative t-axis. Okay, so the blue lines intersect the gamma curve only on the x-axis. The purple lines intersect the gamma curve only on the positive t-axis. So this is good because remember in the existence and uniqueness video I mentioned that we need to have it so that the characteristics only intersect the characteristic curve, or sorry, the gamma curve once, at least to get global solutions. In addition to that, the really important thing is that we can see that every point in the xt plane is going to be on exactly one of these characteristics. For every point, one of these lines is going to go through it. It's either going to be a purple line or a blue line, or this one line here is going to be a purple-blue line. Okay, so let's see how this is going to go. I'm going to use this side of the board to solve these equations. Okay, I'll probably do my work over here and then put the solutions over here. So in purple, what's going to happen? Well, if I pick a point, a generic point, if I pick a generic point here, xt, and then this would be the corresponding t naught, then u of xt is going to be equal to e to the s. So just, if I start here, going the distance there to e to the s. Okay, well, I need to find what e to the s is. So I've got x is equal to s, and t is equal to s plus t naught. Notice t naught doesn't appear here in this expression. X is equal to s, so e to the x is equal, u of xt is equal to e to the x. So I'm going to call this ua of t. So ua of t is equal to e to the x. Ua of t is equal to e to the x. That makes no sense. Ua of xt is equal to e to the x, and this is valid for points that are above this line right here. So this is going to be for t greater than or equal to x. All of these points up here, we're going to have ua of xt is equal to e to the power of x. Okay. So that's what happens if we are on a purple curve. So if we are below the line, if we are below this line here, as you can see, the characteristic it's going to lie on is going to be one of these b characteristics. Okay. So I'm going to call this point, this generic point xt. We're going to trace it back to this point, and now we see that u of xt is going to be equal to 1 plus x naught times e to the s. Okay, well, just like we've done, we need to figure out what s and x naught are in terms of x and t. Well, we have x is equal to s plus x naught. We have t is equal to s, so this is equal to t plus x naught. So we see that x naught is equal to x minus t, x naught is equal to x minus t, and s is equal to t. So we have ub of t, ub of xt, I don't know why I said that again, is going to be equal to 1 plus x naught, where x naught is equal to x minus t. So this is 1 plus x minus t times e to the power of t. Times e to the power of t, and this is going to be for t less than or equal to x. That's going to be for t less than or equal to x. Okay, so what I'm going to do now is I want to talk about this solution a little bit, but I need more room, so I'm going to basically erase everything and keep that there. So sketch these characteristics if you want to be able to refer to them as I go on here. So then our solution, our overall solution, is going to be u of xt is equal to e to the x when t is greater than or equal to x, and then I'm going to say it's 1 plus x minus t e to the t, and here I'm going to say when t is strictly less than x. Okay, but a question that we want to ask is this solution continuous, and is it continuously differentiable? So is it continuous, and is it continuously differentiable? Well, we know that this is continuous on the part of the plane that's above that line, t is equal to x. This is continuous on the part of the plane that's below that line, t equals x. So what we now want to see is that if it's continuous across that line. In other words, if t is equal to x and I plug in t equals x here and t equals x here, are they equal to each other? And the answer is yes. If you plug in, if you look at ua of xx, so we're saying that t is equal to x, so ua of xx, we just get e to the x, and ub of xx, again we're saying t is equal to x. What do we get? Well, it's going to be 1 plus x minus x times e to the x, which is e to the x. So the answer is yes. If you look at the limit of ua approaching the line x equals x, or the limit of ub approaching the line, x equals t, or ub approaching the line x equals t. They're equal to each other, and so they're continuous. Okay, but the next question is, what about in terms of the derivatives? Are the derivatives continuous? Well, again, we know this derivative is continuous on the part of the plane above the line t equals x. This is continuous. The derivative of this is continuous on the part of the line below t equals x. So let's see if they're going to be, if the derivative is continuous on the line t equals x. In other words, if I take the x derivative of this, is it equal to the x derivative of that when I plug in x is equal to t? If I take the t derivative of this, is it equal to the t derivative of that when I plug in x is equal to t? Notice that I have to do the derivative and then I can plug in x equals t. I can't plug in x equals t here and then do the derivative. So I need to do the derivative and then plug in x equals t. Okay, so the x derivative of ua of xt is equal to e to the x, and the x derivative of ub of xt, okay, well, it's going to be the derivative of this with respect to x, which is just 1 times e to the t, which is e to the t. And if x is equal to t, these two things are equal to each other. So we see that the x derivatives are equal to each other on the line t is equal to x. So in other words, the x derivatives are continuous. Okay, what about the, so now let's think about the t derivatives. If you look at the t derivatives ua of xt, well, that's just equal to 0 because it doesn't depend on t. And then t derivative here, the t derivative of ub of xt, okay, well, what are we going to get? It's going to be the derivative of this with respect to t, which is minus 1 times e to the t, plus this, which is 1 plus x minus t, times the derivative of e to the t, which is just e to the t. And now we get that the t derivative, if we plug in t is equal to x, what are we going to get? Well, this is going to be equal to minus e to the x plus, okay, x minus x, that's going to be equal to 0. So it's just going to be plus 1 times e to the t, or 1 plus e to the x, which is equal to 0. And now we see that, yes, in fact, what is going to happen here is that the t derivatives are also going to be continuous across this line t equals x as well. So what about the second derivatives? So again, let's look at the x derivative of ua of xt is equal to e to the x, and I think you can see that the double x derivative is also going to be equal to e to the x. If we just keep doing the x derivative, that's what we get. If we do the x derivative of ub of xt, well, what do we get? Well, it's going to be e to the t. We got that before. Well, if you do the double x derivative, there's no x's there. So this is equal to 0. And now we see if we plug in x is equal to t, these two are not equal to each other. So in other words, the second derivatives are continuous for t greater than x. They're continuous for t less than x, but they are not continuous through the line t is equal to x because these don't match up with each other. Okay, so this is just one of the things that happens when we're dealing with first order differential equations. The most that the existence and uniqueness theorem guarantees us is that we are going to get functions that are continuously differentiable, once continuously differentiable. That's what we found here. But here they are not, the second derivatives are not continuous. They are not twice continuously differentiable. So again, unlike the diffusion equation, Laplace's equation, Poisson's equation, there's no smoothing that happens here. Okay, we start with this, and the solution that we get here is not even twice continuously differentiable, even though, like, you know, all of these coefficients are great. This is a linear, like, it's a very linear, system of differential equations here. So the point that I want to emphasize here is just that things are harder when we do PDEs. Maybe more interesting, but things are harder when we do PDEs, and things that are just kind of definitely true for ODEs are no longer true for PDEs, even for problems that are not like hard problems. Like there's no nonlinearity here or anything like that. Okay, that's all.